Welcome back. Let's practice working with cylindrical coordinates. All right, so here's our first example. We want to plot the points in the cylindrical coordinate system. And we have 5 different points that we want to plot. Points A, B, C, D, and E. Let's start with point A. We have the point 1, pi divided by 2, 0. Remember that for a set of cylindrical coordinates, the first coordinate is the radius, the second coordinate is the angle, and the third coordinate is the z-coordinate. All right, so the first 2 coordinates are essentially the same as a polar coordinate that we would plot in the xy plane. And then once we have that point plotted, we either shift it up or down along the direction of the z-axis, and that will be our point in the cylindrical coordinate system. Now in this case for point A, the z-coordinate is 0, so that means we're not going to go up or down along the z-axis. We are going to stay in the xy plane. We're not going to go above or below it. So this is a pretty simple point to plot. It's basically just a polar coordinate. We have a radius of 1 and an angle of pi divided by 2. Now remember, we measure all of our angles from the positive x-axis where we have an angle of 0. So an angle of pi divided by 2 takes us to this angle right here, the positive y-axis. So we know we're going to be along this angle and have a radius of 1. So we'll be along the first circle. So that means point A would be right here. Okay, so that's point A. That was pretty simple. But now let's move into point B where we actually have a z-coordinate, right? This time we have 2, pi, and then 3. So our radius is 2, our angle is pi, and our z-coordinate is 3. So let's start with the angle. We want to measure an angle of pi from the positive x-axis. So that will take us to this angle right here, which is essentially the negative x-axis. Our radius is 2, so we're going to be along the second circle here. So right at this point, that would actually be the shadow or the projection of our point in the xy plane. But since we have a z-coordinate, that's not where the actual point will be. It's going to be above the xy plane, particularly 3 units in the z direction above the xy plane. All right, so the way that we account for that coordinate is to first draw a line parallel to the z-axis from our projection of the point, or I like to call it the shadow point, because if our point had a shadow in the xy plane, that's where it would be. And then from our z value of 3, because that's the z-coordinate, we want to draw a line parallel to the angle of our point. So that will look something like this. And then where those 2 lines meet is where your point will be. So right here is our point B. And then if you want, you can clean it up a little bit, erase a little bit of those extra lines, and there you have it. That's point B. Let's move on to our next point, point C. We have negative 3 pi divided by 3, and then negative 2. So the radius is negative 3, the angle is pi divided by 3, and the z-coordinate is negative 2. So we will be below the xy plane this time, but before we do that, let's take care of the radius and the angle. The angle is pi divided by 3. That is 1/3 of the way to pi. So you're not going to reach pi divided by 2. That would be halfway to pi. Pi divided by 3 is a little bit less than that. So I'll say that the angle pi divided by 3 is right about here. We'll say that that's pi divided by 3. So we will be along that angle. But then what about our radius? It's negative 3. So what does that mean? Well, it means we're going to be along the third circle that represents a radius of 3. But instead of being right here along the radius of 3 at this angle, what we want to do is reflect it to the other side of the xy plane. So if we extend our angle here, essentially what we are doing is we're just adding an angle of pi to our angle. So we'll go from pi divided by 3 to 4 pi divided by 3. That would be the angle over here. And so our point C is going to have a shadow or projection in the xy plane right here. Okay, so once again, we went to an angle of pi divided by 3, and then we have a radius of 3, but that radius is negative, so we reflect to the other side of the xy plane, and so that is the shadow of our point. Now what we need to do is account for our z-coordinate. We need to go 2 units down in the z direction. So I'll draw a line from our shadow parallel to the z-axis, and then you want to draw a line parallel to the angle from the z-coordinate, which is negative 2. So that'll look something like this, and then where those 2 lines meet is where our point C will be. Okay, so that's point C. Let's move on to point D. We have 4 negative pi divided by 6, and then 1. So the radius is 4, the angle is negative pi divided by 6, and the z-coordinate is 1. So once again, we will be above the xy plane. We're going in the positive z direction. The radius is 4, so we will be along the fourth circle. But what about our angle? It's negative pi divided by 6, which seems tricky at first, but remember that if the angle is negative, you're just going to be measuring it in the opposite direction. All right, so typically when we measure angles, we go this way, right? We go to pi divided by 2, then pi, then 3 pi divided by 2, then 0, or essentially 2 pi. And so if we have a negative angle, we're going to go the other way. So we would go negative pi divided by 6 in this direction, which if this is 0 or 2 pi, because that would represent a full circular motion, you could just subtract pi divided by 6 from 2 pi to figure out what angle that would be. And 2 pi is the same as 12 pi divided by 6. So if you subtract 1 pi divided by 6, that takes you to 11 pi divided by 6. So our angle here is 11 pi divided by 6. Okay, so we're going to be along this angle at a radius of 4. So our shadow point would be right here. That's the projection of point D in the xy plane. Now what we need to do is move it up 1 in the z direction because our z coordinate is 1. Okay, so I'll draw a line parallel to the z-axis and then a line from the z value of 1 that is parallel to our angle. And so you want to look at this angle right here, 11 pi divided by 6. So we'll draw a line parallel to that, and then where those two lines meet is where point D will be. Okay, so that's point D. Now let's look at our last point, point E. And point E is -2, -3 pi divided by 4, and -3. So the radius is -2, the angle is -3 pi divided by 4, and the z-coordinate is -3. Let's start with the angle. -3 pi divided by 4, we would be measuring 3 pi divided by 4 in this direction. So where would that take us? Well, it's not going to take us all the way to pi, right? Because 3 pi divided by 4 is less than pi. In fact, it will take us 3/4 of the way to pi in this direction. So we're looking at an angle right here that's halfway between 3 pi divided by 2 and pi. And so that would actually be 5 pi divided by 4. So I'll write that down. An easy way to figure out what that angle would be is just to add 2 pi to your negative angle. All right, if you add 2 pi to -3 pi divided by 4, you will get 5 pi divided by 4. All right, that's just a quick tip if you didn't know that. That's the easiest way to probably go about that. But that's where our angle is. And our radius is -2. So we are going to be along this angle, but on the other side of the coordinate plane. We're going to be along the second circle that represents a radius of 2, but because that radius is negative, we need to reflect over here. So let's continue our angle this way and figure out what that angle would be. You just want to subtract pi, all right? Because if you're going from one side of the coordinate plane to the other, and that coordinate plane is a polar coordinate system, which is what we have in a cylindrical coordinate system, the xy plane deals with polar coordinates, going from one side to the other is an angle of pi. So you just subtract pi from 5 pi divided by 4, and you get an angle of pi divided by 4, exactly in between 0 and pi divided by 2. So we're going to be along that angle at a radius of 2. So right here is the shadow point for point E. Now what we need to do is adjust for the z-coordinate, which is -3. So what I'll do is draw a line parallel to the z-axis from that projected point, and then you want to draw a line parallel to the angle from the z value of -3. Now our angle is pretty steep here, so make sure to make a line parallel to that. It will be something like this. So our two lines intersect right here, so that will be point E. Okay, and that was the last point that we needed to plot, so we have completed this example. We have now plotted all 5 of these points in the cylindrical coordinate system, and so we're done. The most important thing to remember here is that this really isn't any different from plotting in a polar coordinate system, except you're just adjusting for the height of your coordinate. All right, that's what that last coordinate is. It's a z-coordinate, so you plot a polar coordinate as usual, and then you just adjust for the z direction. Okay, let's look at a different example. Next up, we want to find another set of cylindrical coordinates that represent the same point. And we have 3 different points that we've been given. Now, what this is referring to is the fact that cylindrical coordinates are not unique. In other words, you can represent the same point in a cylindrical coordinate system with a multitude of different coordinate values. Okay, there's multiple different sets of coordinates that represent the same point. Just like in a polar coordinate system in 2 dimensions, points are not unique. There are an infinite number of sets of a radius and angle that will get you to a particular point in the polar coordinate system. And that same idea applies here. Okay, and so for a problem like this, there is an infinite number of correct answers. I'm going to give you a correct solution here, but it's not going to be the only correct solution. You could find so many other sets of cylindrical coordinates that would represent the same point that we've been given here. Okay, and I'll explain how that's possible in just a second. But let's take a look at our first point. We have 3, pi, and 2. All right, so our radius is 3, our angle is pi, our z-coordinate is 2. The easiest way that you can find another point, an equivalent point in the cylindrical coordinate system, is to simply just add 2 pi to the angle. All right, so my answer here is going to be 3, and then 3 pi, and 2. That is a set of cylindrical coordinates that represents the same point. Now, how do I know that? Well, if you think about it, ignoring the z value for a second, if we were to plot this point in this coordinate system, we have an angle of pi, so we'd be going to this angle right here, and we have a radius of 3, so we'd be right here along that third circle. But then if you add 2 pi to the angle, well, that's just a full circle, right? So you're right back to where you started. An angle of 3 pi in the xy plane here is just going to take you right back to that angle of pi. Okay, and I'm going to do the same thing for the second point here. We have 2 negative 3 pi divided by 4, and then a z-coordinate of 0. We can find another set of cylindrical coordinates that represents the same point by just adding 2 pi to the angle. All right, so if I do that here, our new point will be 2, 5 pi divided by 4, and then 0. Remember that 2 pi would be the same as 8 pi divided by 4. So if you take 8 pi divided by 4 and subtract 3 pi divided by 4, you get 5 pi divided by 4. Okay, so that is another set of cylindrical coordinates that represents the same point as this one. All right, and then finally, let's look at our third point here. I'm going to use a different strategy this time. You could certainly just add 2 pi to the angle again, but there is another option. Something else that we can do is negate the radius and then add pi to the angle. Or really, you could add any odd number of pi's to the angle. Okay, but I'm not going to make it more complicated than it needs to be. Why add 3 pi when you can just add pi? So an equivalent set of cylindrical coordinates here would be positive 1, 5 pi divided by 6, and then negative 3. You don't change the z-coordinate, that stays the same. That is another set of cylindrical coordinates that represents the same point. We negated the radius, so we went from negative 1 to 1, and then added pi to the angle, so pi divided by 6 becomes 5 pi divided by 6. Okay, the rules that I was using in this example are summarized by this. A set of cylindrical coordinates would be equal to that same set, but where you add 2 pi to the angle, or you could take that same set of coordinates, negate the radius, and add pi to the angle. Okay, now in my lesson video, I show a generalized form of these rules where really you can add any multiple of 2 pi to this angle and you'll still get the same point, or you can add any amount of odd numbered pi's to this angle. As long as you negate the radius, you will still be representing the same point. Okay, and just to reiterate that this last rule is true, we use the last rule for this point here. If we ignore the z-coordinate and we just look at the xy plane where we're working with polar coordinates, an angle of pi divided by 6 will take you back here somewhere. We're moving an angle of pi divided by 6 in this direction. So that would be somewhere about here. And then because our radius is negative 1, we would be along the first circle, but we would reflect to the other side. So we would be at an angle in this quadrant. But if you negated the radius, you would still be over here. And then if you add an angle of pi, well, that just takes you halfway around the circle, so you still end up at the same spot. Okay, so really that's all that's going on here. Just like adding 2 pi to the angle doesn't change the point, adding pi to the angle and then negating the radius doesn't change the point either. The coordinates are different, but they represent the same point. Okay, let's move on to a different example. All right, so for the rest of the examples in this video, we are going to be focusing on converting from cylindrical coordinates to rectangular coordinates. We will start by just looking at sets of coordinates. We will convert points from cylindrical to rectangular and vice versa. And then we will look at some equations in cylindrical coordinates and rectangular coordinates and convert them to the other form, right? Whatever form we are given, we're going to convert it to the other form. Okay, and so I have all of our conversion formulas in this sidebar here. Remember that x equals r times cosine theta, y equals r times sine theta, r squared equals x squared plus y squared, tangent theta equals y divided by x, and the hardest one of them all, z equals z. Hopefully you don't forget that one. The z coordinate will never change when you are converting from cylindrical to rectangular or vice versa. The z coordinate stays the same. Okay, I show where all these formulas come from in my lesson video, but in this video, we're just worried about using them. So let's take a look at what we have here. We want to convert the point from cylindrical coordinates to rectangular coordinates. So that would be this point right here. Now, upon first glance, it looks like it is a set of rectangular coordinates because the angle doesn't really jump out at us because you don't see pi anywhere, right? The angle is 0. This is a set of cylindrical coordinates where the radius is -8, the angle is 0, and the z-coordinate is 10. All right, in fact, I'm going to write that down here so we don't forget. R is equal to -8, theta is equal to 0, and z equals 10. Now, when you do these problems, it can be helpful to know where your point is located generally in the 3D coordinate system or in your cylindrical coordinate system. And what I mean by that is just be aware of what quadrant and octant your point is located in. So in this case, if our angle is 0, we're going to be along this angle right here, but our radius is -8. So we would be at a radius of 8, but we need to reflect to the other side. So we'd be along this angle of pi, and then we would go up 10 units in the z direction. So we know that our point is somewhere over here. Particularly, it's along an axis, so it's not really in a specific quadrant or octant, but at least we have an idea of the location of that point. Okay, so hopefully whatever point we get when we do our conversion here, that will be in the same area, or in fact, it will be the same exact point. We just want to make sure that that's where it is. Okay, so let's do our conversions here. To get to rectangular, we need to switch from values of r and theta to values of x and y. So we want to use these two equations because we want to solve for x and y. So we'll have x equals r times cosine theta, so -8 times cosine of 0, and then we'll have y equals r, which is -8, times sine of theta, which is 0. Now cosine of 0 is 1, so x is equal to -8 times 1, which is -8. And then sine of 0 is 0, so y is equal to -8 times 0, which is 0. And then, of course, z is still going to be equal to 10. That doesn't change. There's no conversion formula for that. It's just z equals z. Okay, and so now we have our three coordinates. X is -8, y is 0, and z is 10. So putting them together, we get -8, 0, 10. And would you look at that, we got the same exact point, right? That's exactly what we started with. -8, 0, 10, -8, 0, 10. So kind of weird, but this does happen when your angle is 0. Your point in rectangular coordinates will look exactly the same as your point in cylindrical coordinates. Okay, so kind of a neat thing that happens, but let's take a look at an example where the coordinates will be different. Once again, we want to convert the point from cylindrical coordinates to rectangular coordinates, except this time our angle is not 0. We have 6, -pi divided by 4, and then 2. So for this set of coordinates, r is equal to 6, theta is equal to -pi divided by 4, and z is equal to 2. Okay, now before we do anything, let's figure out where this point would be in our 3D coordinate system. The angle is -pi divided by 4, so we will measure that in this direction. -pi divided by 4 is just halfway to this angle. All right, so we know we're going to be in this quadrant of the xy plane. Our radius is 6, so we're not going to leave that quadrant. We're not going to be reflecting or anything. The radius is positive. So we know we're going to be in this quadrant, which is the fourth quadrant, right? This would be the first, then the second, third, and fourth. And we're not going below the xy plane. We're going above because the z-coordinate is positive. So our point would be in this quadrant, but then it would be up in the z direction. So it's somewhere over here, and we know that it's in quadrant 4, octant 4. Okay, because the octants above the xy plane are 1, 2, 3, and 4, and then below it's 5, 6, 7, 8. So whatever point we get in rectangular coordinates should be in that same area. Or really, it's the same exact point, but we're not trying to be perfect with our sketches here. I'm just trying to make sure that the answer I get makes sense. All right, but now let's actually do our conversion here. Once again, we want to get our coordinates in terms of x and y, so we want to use these two conversion formulas. Let's start with x. We have x is equal to r times cosine theta. So we'll have 6 times cosine of negative pi divided by 4. And then we'll have y equals r times sine theta. So we'll have 6 times sine of negative pi divided by 4. And then we know z is going to be the same. Z is equal to 2. Now, cosine of negative pi divided by 4 is equal to the square root of 2 divided by 2. So this will be equal to 6 times the square root of 2 divided by 2. And 6 divided by 2 is 3. So this is equal to 3 square roots of 2. And then for y, sine of negative pi divided by 4 is the negative square root of 2 divided by 2. So this is equal to 6 times the negative square root of 2 divided by 2. 6 divided by 2, once again, is 3. So this is equal to negative 3 square roots of 2. Okay, so those are our three coordinates. Now let's put them together. We have x equals 3 square roots of 2, y equals negative 3 square roots of 2, and z equals 2. So we'll have 3 square roots of 2, negative 3 square roots of 2, 2. So that's my final answer here. Let's just make sure it makes sense though. If we have a positive x coordinate, we're going to be along the positive x-axis. We have a negative y coordinate, so we're going to be along the negative y-axis. So our point's going to be somewhere within this quadrant. That's good. But then we would raise it up 2 units in the z direction. So it should be the same point. All right, let's take a look at another example. Okay, so this is where things are going to start to get a little bit trickier because now we're doing the opposite conversion. We want to convert the point from rectangular coordinates to cylindrical coordinates. And we have the point 1, square root of 3, 4. Okay, so the last two examples we were converting from cylindrical to rectangular. Now we're doing the reverse. So in this case, x equals 1, y equals the square root of 3, and z equals 4. Now let's make sure we know where this point is in the 3D coordinate system. If all three coordinates are positive, then that's pretty simple. We know we're in the first quadrant of the xy plane and the first octant of the 3D coordinate system. So we know our point will have a shadow somewhere in this plane, and it will be up in the z direction. So that's about where our point would be. Obviously, that's not exact. I'm not really measuring any of these coordinates. I'm just getting an idea of where that point is located in terms of quadrants and octants. Okay, and in this case, we are in quadrant 1, octant 1. So when we get our point in cylindrical coordinates, we want to make sure that that is also in that quadrant and octant. Okay, that's just going to help us match the right angle to the right radius. And you'll see what I mean when we get to solving for r and theta, which, speaking of which, we can do that right now. We currently have coordinates in terms of x, y, and z, so we want to get coordinates in terms of r, theta, and z. So because we want to know r and theta, we should use these two conversion formulas that allow us to calculate them using x and y. First up, we have r squared equals x squared plus y squared. So we'll have 1 squared plus the square root of 3 squared. 1 squared is 1, and the square root of 3 squared is 3. So r squared is equal to 1 plus 3, so r squared equals 4, which means that r equals plus or minus 2. So we get two different values for the radius. We'll talk about what that means in a little bit, but for now let's focus on the angle. We're going to have tangent theta is equal to y divided by x. So we have the square root of 3 divided by 1. And so then that means that theta would be equal to the inverse tangent function of the square root of 3. And you could plug this in your calculator, but the way that I like to think about this is what angle for tangent gives you the square root of 3. And if we're looking at angles between 0 and 2 pi, there's two choices. Theta could be equal to pi divided by 3 or 4 pi divided by 3. All right, so those are your two choices for what angle plugged into the tangent function gives you the square root of 3. Now, we know that z equals 4. Let's just write that down. Z is not going to change. But how do we choose between these two values of r and these two angles of theta for our point? Well, you want to make sure that whatever you pick, it's going to put your point in the right area. We know that in rectangular coordinates, our point is in the first quadrant and the first octant, so we want the same thing for our point in cylindrical coordinates. And so looking at these two angles, which of these angles is going to get us in the first quadrant? Pi divided by 3 or 4 pi divided by 3? Hopefully you said pi divided by 3, right? If you go to 4 pi divided by 3, you're going past pi, you're going to be out here somewhere. We just want pi divided by 3 because that is in between 0 and pi divided by 2. Okay, pi divided by 3 is a third of the way to pi, while pi divided by 2 is halfway to pi. So a third is less than a half. So it's going to be in here somewhere. That's good, that's where we want it. So what we want to do is match that up with our positive radius so that we're not reflecting to the other side, we're staying in the right quadrant. So our answer here will be a radius of positive 2, an angle of pi divided by 3, and a z-coordinate of 4. However, there are many other possible answers here because as you saw in a previous example in this video, there are an infinite number of sets of cylindrical coordinates that represent the same point. So what we could do here is make use of our other angle for pi divided by 3. That's an angle of pi greater than pi divided by 3, right? So we said that pi divided by 3 was over here, which means that 4 pi divided by 3 is over here. So if we make our radius negative, then our point would flip back to be in the first quadrant, which is where we want it. So another point that we could set up here is to have a negative radius, so negative 2, and then that angle of 4 pi divided by 3, and then the z-coordinate of 4. Either or, both of those answers would be right, all right? And they're not the only right answers. You could add 2 pi to these angles over and over and over again to get more and more points. But we just want the nicest points, which is what we found here. Okay, and so you can see one of those other rules that we worked with earlier is true. If you negate the radius, you get negative 2, and so then you would want to add pi to the angle, and pi divided by 3 plus pi is 4 pi divided by 3. So we know that these two sets of cylindrical coordinates represent the same point. Okay, let's take a look at another example of converting from rectangular to cylindrical. This time we want to convert the point from rectangular coordinates to cylindrical coordinates, and our point is 4 square roots of 2, 4 square roots of 2, negative 5. All right, so this is a point in rectangular coordinates, which means that x equals 4 square roots of 2, y equals 4 square roots of 2, and z equals negative 5. All right, now where in our 3D coordinate system is this point located? Well, both x and y are positive, so we know we're going to be in the first quadrant, but then the z-coordinate is negative, so we will be going below the xy plane, so we're going to be in the 5th octant. So we know that our point would be projected into the xy plane somewhere there, and then we'd go below the xy plane to right here, okay? And so that point is in quadrant 1, octant 5. Okay, so you want to keep that in mind when we choose our angle and radius value. But now let's find them. Let's find r and theta. Once again, we want to use these two conversion formulas, r squared equals x squared plus y squared, and tangent theta equals y divided by x. We'll have r squared is equal to x squared, so we have 4 square roots of 2 squared plus y squared, so we have 4 square roots of 2 squared, and then if we simplify, 4 squared is 16, the square root of 2 squared is just 2, so r squared is equal to 16 times 2 plus 16 times 2. 16 times 2 is 32, and so if you add 32 to itself, you get 64. So r squared equals 64, which means r equals plus or minus 8. So those are our two radius values to pick from. Now let's work with the angle. We know that tangent theta is equal to y divided by x, and y and x are the same, right? We have 4 square roots of 2 divided by 4 square roots of 2. So we know that theta is equal to the inverse tangent function of 1, or arctangent of 1. So you can put that in your calculator if you'd like. But once again, I recommend that you just think about it like this. What angle of theta, when I plug into the tangent function, gives me 1? And in this case, that would be pi divided by 4 and 5 pi divided by 4 if we're just thinking about angles from 0 to 2 pi. Okay, so from this, we know that theta is equal to pi divided by 4 or 5 pi divided by 4. Now, I believe if you put it in your calculator, you would just get pi divided by 4. That's fine. As long as that angle is in the right quadrant of where you know your point should be, you can use that angle and pair it up with your positive radius, and you're good to go. I'm just trying to show you a more in-depth way of going about this problem, if that's something that helps you understand kind of what we're doing here. Okay, but if you're just looking for a quick method, yes, you can plug it in your calculator, get that one angle, just make sure it's in the right quadrant. If not, you can add pi to it or make any adjustments you need to make so that the point is in the right quadrant. Okay, but looking at these two angles we have here, which one of these angles does take us to the first quadrant? Well, it's pi divided by 4, right? It's not going to be 5 pi divided by 4. That's more than pi, so we would be somewhere in here. That's not where we want to be unless we make our radius negative. Then we would be back to where we want to be. And so putting that information together, we can come up with two different points here. And of course, these are just two of many different answers that you could have. We'll have positive 8 positive pi divided by 4, and then our z coordinate, it didn't change, it's still going to be z equals -5, so we'll keep that. And then our other point would be -8, 5 pi divided by 4, -5. Okay, you really only need one for these problems, but I am giving you two so that you can see potentially some different answers that you could get. But if you're doing these problems on your own, you really only need one answer. I'm just giving you some different options. Okay, but with that, this was the last example for converting points from rectangular to cylindrical and vice versa. Now what I want to do is look at some equations in rectangular and cylindrical and convert those. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. First up, we want to find an equation in cylindrical coordinates for the equations given in rectangular coordinates. So very clearly, these are rectangular equations, right? We have x equals 9, y equals 5, z equals 4. They deal with x, y, and z. In fact, you might even recognize that these represent planes in the 3D coordinate system, right? Whenever you just have a single variable to the first power, x, y, or z, equal to some constant, that represents a plane. Now to convert these two equations in cylindrical coordinates, we need to use our conversion formulas. Let's start with x equals 9. We want to replace x with r times cosine theta. So we'll have r cosine theta equals 9. And then typically you want to solve for r. That's usually the way we go about cylindrical equations. You don't always have to solve for r, but when you can, you should do it. So in this case, we want to divide both sides by cosine theta. So we'll have r equals 9 divided by cosine theta. And then we know that 1 divided by cosine theta is secant theta. So r is equal to 9 times secant theta. Okay? So that's our first cylindrical equation. That corresponds to x equals 9. Now let's work on y equals 5. It's going to be a very similar process, except instead of replacing it with r cosine theta, we know that y is equal to r sine theta. So we'll have r sine theta equals 5. If you divide both sides by sine theta, you'll have r equals 5 divided by sine theta. But we know that 1 divided by sine theta is cosecant theta. So we could write this as r equals 5 times cosecant theta. Okay, so that's the equation that's equivalent to y equals 5, but in cylindrical coordinates. And then finally, let's convert z equals 4. Don't think too hard about this one. If z is equal to z between rectangular and cylindrical coordinates, then the equation z equals 4 is still going to be z equals 4. Okay, so nothing changes here. Z is still going to be equal to 4. That is the equation in cylindrical coordinates for that plane. All right, so these three equations are equivalent to their corresponding equations above, and they all represent planes in the 3D coordinate system. Let's look at another example. Next up, we want to find some more equations in cylindrical coordinates for the equations given in rectangular coordinates. All right, so we're still going from rectangular to cylindrical. We did not switch yet. We have x² plus y² equals 8x, and z² equals x² plus y² minus 11. Let's start with this one. We know that x² plus y² is equal to r², so that's pretty easy to convert to cylindrical. We'll have r² equals 8 times x. Let's just replace x with r times cosine theta. So we'll have 8 times r cosine theta. Now we have a common factor of r on both sides of the equation, so we can cancel those out and just have r equals 8 times cosine theta. And that would be the equation in cylindrical coordinates. Now let's look at this one here. We have a very similar conversion. z² equals x² plus y² minus 11. We can replace x² plus y² with r². So we'd have z² equals r² minus 11. And really, you could leave it like that. That would be your final answer. But like I said earlier, if you can solve for r, you should, or at least solve for r². So if we add 11 to both sides of the equation, you'll find that r² is equal to z² plus 11. Now, I would recommend you keep it like this, That's typically how you will see an equation like that represented. I suppose you could write r equals the square root of z² plus 11, but generally you just want to leave it as r² if you can't reduce it by a factor of r like we could in this case. Alright, leaving it like this is totally fine. Let's look at some more examples. Once again, we want to find an equation in cylindrical coordinates for the equations given in rectangular coordinates. This time we have x² plus y² plus z² equals 13 and y equals x². This is not a requirement for these examples, but this equation right here, you can recognize to be a sphere, right? We have x² plus y² plus z² equals some radius squared, where the radius in this case would be the square root of 13. Like I said earlier, that's not really important to this example, but I just wanted to point that out. This is clearly a sphere that we're working with, but to convert it to cylindrical coordinates, all we have to do is replace x² plus y² with r². So we'll have r² plus z² equals 13. And that's fine, but like I said in the previous example, if you can solve for r or r², you should. So in this case, you want to subtract z² from both sides of the equation, and you'll get r² equals 13 minus z². And that would be our equation in cylindrical coordinates. Okay, that would also represent a sphere with a radius of the square root of 13. Okay, and if you wanted to, you could write r equals the square root of 13 minus z², but generally you just want to leave it as r². You don't have to do this. Okay, and then let's move on to this one. We have y equals x². This is a little bit trickier. We have x², but it's not paired with a plus y², so we cannot replace that with r². Okay, we have to go about this a little bit differently. I'm just going to replace y with r times sine theta and replace this x with r times cosine theta. So we will have to square r and cosine theta. All right, so we'll have r times sine theta equals r times cosine theta squared. Now, if you square each part, we'll have r times sine theta equals r² times cosine squared theta. Now, you want to try to simplify this a little bit more. First thing I see is that we have a common factor of r that we can cancel out. So we'll just have sine theta equals r times cosine squared theta. And now we can solve for r if we divide both sides by cosine squared theta. Doing so will give us that r equals sine theta divided by cosine squared theta. And we can simplify that even further. If I rewrite it like this, we'll have sine theta divided by cosine theta times cosine theta, right? That's what cosine squared theta is. It's just cosine multiplied by itself. We know that sine theta divided by cosine theta is tangent theta. So we'd have r is equal to tangent theta times 1 divided by cosine theta. But we know that 1 divided by cosine theta is secant theta. Okay, so I'm just going to write it like this. Our final answer is that r equals tangent theta times secant theta. And that would be the equation in cylindrical coordinates that is equivalent to y equals x². And I didn't really mention it, but just like I said that this represents a sphere, this right here, this equation, represents a cylinder, particularly a cylinder directed along the z-axis that has a trace of a parabola in the xy plane. Okay, so not really important to this example, but I did just want to point that out. That's what that represents. And we can represent that same surface in cylindrical coordinates with r equals tangent theta times secant theta. Let's move on to the next example. From here on out, we are switching things up. Instead of converting from equations in rectangular coordinates to cylindrical, we're going to be converting equations in cylindrical coordinates to rectangular. You can see that we have some equations in terms of r, theta, and z right here. Okay, so we want to find an equation in rectangular coordinates for the given equations in cylindrical coordinates, and we want to identify the surfaces. Okay, essentially what I'm saying is, can you identify what they represent in 3D space? You don't have to graph it, just determine the shape or the type of the surface. All right, and so let's start with r equals 6. To convert that into rectangular, I would prefer if that r was squared, because r² equals x² plus y². So let's square both sides of the equation. That'll give us r² equals 6², which is 36. And then we can replace r² with x² plus y². So we'll have x² plus y² equals 36. And that would be the equation in rectangular coordinates. Now, what does it represent? Well, it represents a surface, but what type of surface? Notice that there's only two variables in the equation. So that means it represents a cylinder or a cylindrical surface. Particularly, it's a cylindrical surface with a trace in the xy plane of a circle, right? This is the equation of a circle with a radius of 6. And that trace would be projected along the z-axis because the z variable is not present in this equation. All right, so this is a cylinder with a trace of a circle r equals 6, or the radius equals 6. And if you want to write this down, it is directed along z-axis. Okay, so that's that surface. Let's move on to our next equation. We have theta equals pi divided by 6. So to convert that into terms of x and y, I think we can just plug that into this equation. Tangent theta equals y divided by x. So if we do that, we'll have tangent of pi divided by 6 equals y divided by x. And tangent of pi divided by 6 is the square root of 3 divided by 3. So that would be equal to y divided by x. And then I'm going to solve for y. So I'll multiply both sides by x. And that will give me y equals the square root of 3 divided by 3 times x. And that would be my equation in rectangular coordinates. But now what does it represent? Well, it looks like it would represent a cylinder, right? We have an equation in terms of two variables, x and y. But notice that the trace that it would represent is a trace of a line, okay? This is just a linear equation. So if you projected this along the z-axis, you would just create a plane. All right, so this just represents a vertical plane. All right, I'm not going to get more specific than that. Obviously, the angle of that vertical plane is pi divided by 6, but it's just good to know that that represents a vertical plane. Now, moving on to our last equation, we have z equals 6. Once again, don't think too hard about this. We already did this from rectangular to cylindrical, but now we're doing the opposite, and nothing changes here, right? Z is just equal to z. So this is the equation in cylindrical, but it's also the equation in rectangular. It's just z equals 6. That's it. And what is that? Well, it's a plane that cuts through the value of z at 6, all right? So this is actually a horizontal plane. It is a plane that has all of the points where z equals 6. Okay, and if you watched my lesson video, this should make sense. I showed you that in cylindrical coordinates, if you have z equal to some constant, that represents a horizontal plane. And if you have theta equal to some angle, then that represents a vertical plane. Okay, let's look at some more examples. Next up, we once again want to find an equation in rectangular coordinates for the given equations in cylindrical coordinates, and we want to identify the surfaces that they represent. And our two equations are r² plus z² equals 5, and r equals 1/2 times z. And the first one's pretty simple. We can just replace r² with x² plus y², and we'll be done. So if we do that, we'll have x² plus y² plus z² equals 5. That just represents a sphere, right? Particularly, it's a sphere with a radius of the square root of 5. You just take the square root of the constant that x² plus y² plus z² is equal to. And then let's move on to this equation. We have r equals 1/2 times z. This is going to be a little bit trickier. The first thing I'm going to do here is square both sides of the equation. That way I'll have an r² that I can replace with x² plus y². So if we do that, we'll have r² equals 1/4 times z², right? If you square 1/2, you get 1/4. And then, of course, z² is z². Now, let's replace r² with x² plus y². We'll have x² plus y² equals 1/4 times z². In fact, I'll just write it like this. We'll have z² divided by 4. And that's our rectangular equation, but what does it represent? Well, we can get a better idea if I move this term over to the other side of the equation. Or in other words, if we subtract z² divided by 4 from both sides, we'll have x² plus y² minus z² divided by 4 equals 0. And now, hopefully you can see that we have a special type of surface. It's one of our quadric surfaces. All three of our variables are squared. One of those variable terms is negative, and there's no constant. The variable terms are equal to 0, so it must represent an elliptic cone. All right, I'm not going to get more specific than that. It's just good enough for us to know that we are working with an elliptic cone. Let's take a look at another example. Once again, we want to find an equation in rectangular coordinates for the given equation in cylindrical coordinates and identify the surface. This time we have r equals 2 times sine theta. And you have to be careful here. You might be tempted to just replace sine theta with y, but you can't unless it's multiplied by r. So what we should do here is multiply both sides of the equation by r, And that's actually really nice because it also makes this r become r², which we could replace with x² + y². All right, so multiplying both sides by r is helpful here. We'll have r² equals 2 times r times sine theta, which then will become x² + y² equals 2y. And that right there, if we weren't asked to identify the surface, we could just stop and say, that's the equation in rectangular coordinates. That's fine, but to get a better idea of what this surface is, I think we can take it a little bit further. Obviously, it's going to be a cylinder of some kind because we have an equation with two variables, x and y. There is no z. So it's going to be a cylinder with some kind of trace, but we need to determine what that trace is. And if you're really good with equations, you might already know what this is. You might be able to see that, hey, this is a circle that's not centered at the origin because I have x² and y², and then some other term where one of those variables is to the first power. And so because of that, what we probably want to do here is complete the square for our y terms. So here's what I'm going to do. I'm going to subtract 2y from both sides of the equation. So we'll have x² + y² minus 2y equals 0. And then we want to complete the square here so that we can have a quantity of y plus or minus some value squared. And then we'll be able to see where this circle would be centered. And to complete the square, what we need to do is divide the coefficient of the degree 1 term by 2 and then square it. And that's the value we would need to add to complete the square. So -2 divided by 2 is -1, and -1² is 1. So you want to add 1 to both sides of the equation. That will give you x² + y² minus 2y plus 1 equals 1. And now, these three terms right here can be factored. It would factor to be y minus 1 squared, right? Whatever that value you get when you divided this coefficient by 2, whatever you get for that, in this case -1, that's what's going to be in your factor. So if I continue up here, we'll have x² plus y minus 1 squared equals 1. All right, and now what we have is the equation of a circle, particularly a circle with a radius of 1. You would take the square root of the constant here to get that radius, and it's centered at 0, 1, right? We just have x², so the x coordinate is 0 for the center. And then since you're subtracting 1 from y, the y coordinate of the center will just be +1. Okay, so this is the final form of our rectangular equation, but what it tells us is that we have a cylinder with a trace of a circle with a radius of 1 and a center of 0, 1. And then of course that trace is in the xy plane and is directed or projected along the z-axis. All right, let's take a look at one final example for this video. Okay, so for our last example, we want to find an equation in rectangular coordinates for the given equation in cylindrical coordinates and identify the surface. All right, so it's the same thing we've done for the last couple examples, except we have a different equation in cylindrical coordinates. We have z equals r² times cosine squared theta, and at first this looks pretty tricky. You might be tempted to replace r² with x² + y², but then what do we do about cosine squared theta? That kind of leaves us at a bit of a dead end. I suppose you could solve for theta in this equation and then put arctangent into the cosine function, but that's kind of ugly. We don't want to do that. Instead, hopefully you notice that r cosine theta is equal to x, and since both of those two things are squared, what we actually have here is x², right? So you could rewrite this to be z equals r times cosine theta squared, which is then just z equals x². That is our rectangular equation, equivalent to this equation in cylindrical coordinates. But what does it represent? What is the surface represented by this equation? Well, there's only two variables, so it has to be a cylinder. Particularly, it's a cylinder that has a trace of a parabola in the xz plane, right? Z equals x² is the equation of a parabola. And since we're working with x and z, we know that that parabola would be traced in the xz plane, and it would be directed along the y-axis, or projected along the y-axis to form the cylinder. Okay, and that's the final answer to this example, and this was the last example for this video. However, I do have more examples available on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can find all the details over on my website at jkmathematics.com/plus. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.